All right, so we talked about what the work energy theorem is. Let's now come back and talk about how it is that we're going to use this. So there's basically two ways that we're going to end up seeing. There's two types of problems that we're going to end up seeing where we use the work energy theorem. One is going to be problems where we're given information about all the forces acting on an object and the object's displacement, so we can calculate the net work. The unknown then is going to sit over here in our delta K. And usually it's going to end up being a initial speed or a final speed of the object. The other option, of course, is just, well, if we're given initial and final speeds, then we can figure out the initial and final kinetic energy, which means that delta K is now known. What's not known is going to be something that sits over here on the net work side. So again, usually this will be some magnitude of some force that's acting or some distance that our object travels. The thing I'll go ahead and point out, this is sort of the really useful framework for approaching these problems. Because if we're given both initial and final speeds, then we know which side of the equation we can go ahead and calculate, which means we know that our unknown has to be on the other side. If, on the other hand, I see that I've only got one of my two speeds, then I know my unknown is going to sit over here on the delta K side, and I have to be given enough information to calculate everything about the net work. So even if I don't initially see how, I know that I have to be given that information, because otherwise I've got too many unknowns in the problem. So, as an example, so let's say I've got a 2 kilogram block that's sliding down a frictionless ramp at a speed of 5 meters per second when you begin to push on the block with an applied force of 20 newtons. Your force points up the incline and parallel to the incline. So if your force is directed parallel to the ramp, how far down the ramp will the block slide before coming to a stop? So in terms of what we were talking about before, well, let's look at the problem, and what I recognize is I'm actually given both of my speeds. So the initial speed is easy to see, right? So that's 5 meters per second. So in terms of calculating the initial kinetic energy, 1/2 times the mass, that's 2 kilograms times 5 squared. This happens to just be 25 joules. So I know my initial kinetic energy is a known. Coming to a stop, again, is one of those, I'm not given a value. What I am given is I'm given that value in words, but I recognize that what this means is that the final speed has to be 0, which means the final kinetic energy also has to be 0. So sure enough, I'm given both pieces of information, so that when I look at the work energy theorem, I recognize that I know everything that's going on on the delta K side of the equation, which means my unknown has to be sitting over here on the net work side. And sure enough, my unknown happens to be some distance, how far down the ramp, that will end up over here on this side of the calculation. Second example. So same scenario, I'm going to change the numbers a little bit. So here I've got a 20 kilogram block. It's sliding down a frictionless ramp with some initial speed when you begin to push on the block with an applied force of 20 newtons. You push on the block parallel to the ramp, and the block slides 1.5 meters further down the ramp before coming to a stop. How fast was the block traveling at the instant you began to push on it? So here what I notice is, when I go look for my two speeds, well, coming to a stop, that still means final speed is 0. But all I know is some initial speed. So it seems that my initial speed is unknown, which means all I can do is write this out as 1/2 mv initial squared, and so I don't know my initial kinetic energy. I know how to calculate it, but there's my unknown sitting right there in that initial speed squared. Again, the final speed being 0, I can calculate the final kinetic energy. So when I think about the work energy theorem, what I recognize here is now my unknown is sitting over on the right-hand side. So it's on the delta K side of the equation, which means I have to be given enough information, whether I sort of recognize it initially or not. I have to be given enough information to calculate everything in the net work. So these are sort of the This is a helpful framework for approaching these problems because basically we've got one equation, which means at the end of the day there can only be one unknown. And so figuring out where it sits will kind of help us figure out, well, what's my unknown, where is it, and that means I got to be able to calculate everything else. Here, again, it's easy to see, sure enough, our unknown, how fast was the block traveling? Yep, that's in our delta K. So we're basically solving for the initial speed. All right, so our process for solving problems with the work energy theorem. First thing we're going to do is we're going to draw two pictures because the work energy theorem cares about 2 points. What's going on initially and what's going on at the end. Then we'll go ahead and draw the free body diagram. Now, we're not going to do a vector problem, but drawing the free body diagram will help us keep track of all the forces acting on our object. So we're going to go ahead and draw the free body diagram. Then we'll calculate initial and final kinetic energies. And we're going to start with the K's first because, again, that's going to help us. They're usually easier to find, and that's going to help us figure out where our unknown is sitting in the equation. Then we'll calculate the work done by the individual forces, because almost always that's the way that we're going to approach the net work side of the equation. Then we'll set our equation up. Again, one equation, one unknown, and we'll go solve for what that unknown is. So here's the process that we're going to use. So again, let's take that second example problem I had before. So here's my block. Initially, it's moving with some initial speed, so I don't know what this is. I'm going to start to push on it, and it's going to slow to a stop. So when it's traveled this far down, now it's at a stop. And so it came to a stop because I applied some force that brought it to a stop. I did that over a certain distance, right? So I'm told that the block slides 1.5 meters further down the ramp. So here are my two pictures, right? Initial situation, final situation. I've kind of combined them into one picture here, just because it's easy enough to deal with. And I see that the distance that my block travels from the initial to the final, that's easy to draw in. So this displacement vector has a magnitude of 1.5 meters. So when I draw the free body diagram, well, what forces act on the block? Well, there's a normal force that is perpendicular to the surface. I don't need to worry about friction. There's an applied force that's parallel. There's the weight force that's pointing straight down. So here's my free body diagram. And so now I'll think about my kinetic energies, right? So draw my two pictures, draw the free body diagram, calculate out the kinetic energy. So let's see what I can determine here. In this case, I can't calculate this out as a value because I know my unknown is sitting right there. So the final kinetic energy, because this comes to a stop, I do know this value, so the final kinetic energy is just going to be 0. So I'll leave the initial kinetic energy like this. I'll leave the final kinetic energy, I know that value is going to go ahead and be 0. So the next step is to calculate the individual works. Well, I've got 3 forces, so I need to calculate the work done by all 3 forces. So let's start with the normal. So if I look at the normal, there's the displacement. The angle between those two vectors happens to be 90 degrees, which tells me that the normal force does no work as the block slides down the incline because the normal force is perpendicular to the displacement. So there's one of my 3 forces, easy enough. Second one I'll deal with is let's deal with gravity. So in this case, I know that the gravitational force, well, I calculate the work done by the gravitational force as being plus or minus mg times whatever height that moved up or down. So we'll deal with the plus or minus first. I know it's going to be a plus because I know my box is coming down and gravity does positive work when my box moves down. I need to deal with this h. Well, I wasn't given h. What I was given was d. So I was told some distance along the ramp, but what I want to figure out is what's the change in height. So if I get sort of the rest of this mess out of here for a second, it's easy enough to see that what I've got is a right triangle. I'm told what my angle here is, so I'm told my incline was at a 30-degree angle. Here's my distance d along the incline. Here's the height h that I want. What I notice is that my height side h is opposite the 30-degree angle. D lies along the hypotenuse of that right triangle. So opposite over hypotenuse, that's sine theta. So I can set up this expression and solve it to get that the height is equal to d sine theta. So all I'm basically doing is saying I want h, but I want it in terms of things that I know, and here things that I know are the distance down the incline and the 30-degree angle of the incline. So I can come back and plug that in. So the work done by gravity here is going to be mgd, distance down the incline, times sine of theta. So the last one I need to calculate is the work done by the applied force. The applied force is a constant force, so I know I can calculate it using the magnitude of the force, magnitude of the displacement, sine of the angle between those two vectors. So let me start by drawing those two vectors together, and now I can see what angle phi is. So applied force points up the incline, displacement points down the incline, which means that phi is a 180-degree angle. So the magnitude of the applied force, that's Fa, the magnitude of the displacement, I chose to call that d, and then the sine of phi is the sine of 180 degrees. Well, the sine of 180 degrees is just -1, so I've just brought that out front, and so the work done by the applied force is minus Fa times d. So minus the magnitude of the applied force times the 1.5 meters that the distance slows down, so that the block slides down. So these two I know. 20 newtons, 1.5 meters, to calculate this out. So now that I've sort of done all the individual pieces, I just need to put them together in my equation. So I get that the net work is the work done by gravity plus the work done by the normal plus the work done by the applied force. Delta K is final kinetic energy minus initial kinetic energy. And basically I know what all those terms are. So mgd sine theta, again this theta is not the phi, this is a different angle. This is the angle of the incline. This is mgd sine theta, that's the work done by gravity. Work done by the normal, that was 0. Work done by the applied force was negative, because it's pointing up the incline as the block slides down, so negative magnitude of the applied force times the distance the block slides. Well, that's got to equal 0 minus 1/2 m times v initial squared, and again, v initial is what I want to solve for. So everything else, mass, g, d, theta, Fa, all the rest of those things I know. So there's my one equation, my one unknown. It's fairly straightforward algebraically to solve. I get this expression, go back and plug in the values I'm given, and I get an answer for that the initial speed of the block, when I first start to apply that 20 Newton force to bring it to a stop, it was traveling at 2.42 meters per second. So this is sort of the process that we're going to walk ourselves through to solve problems using the work energy theorem. If you'd like, you can take the first example, and again I'll leave it up to you to go through and work it out and solve, but when you do, you'll get an answer that says how far down the ramp will the block slide before coming to a stop. Well, in this case, that distance is going to be 2.45 meters. So you can work this one. Again, here's you can check your answer and make sure you're getting the right answer. But this will give you a chance to sort of practice before we start using this in class.